and train ourselves to what is coming. So, all yours.
Hi everyone. So yes, I'm Etienne Russeil. I'm a last year PhD student working with Emily at LPC in France. And today I will talk to you a little bit about the Fink effort as a collaboration to work on the ELAsTICC data challenge. So just a little reminder about ELAsTICC. So it is the successor of Plastic, so LSST simulation data. And actually, okay, it's aiming at mimicking as best as possible the alerts from Rubin. And it's very different from Plastic in the sense that it is mimicking the alert behavior in the sense of the stream-like, and it's not only about a full light curve anymore. So it's using the 6 passband of LSST. It is trying to imitate the cadence and the depth. It takes into account extinction and atmospheric noise, and also Host-Galaxy association. And because it's a classification challenge, they propose taxonomy that you can see on the right. And it is tree-based. So it means that you have some broad classes which are divided into small classes. And we've been interested in the broad classes, which are the SN-like object, fast objects, long objects, periodic and non-periodic. And then we've also been interested in the some of the subclasses inside for further binary classifications. So just so that you can get an idea, I show here few examples of light curve like Supernovae 1A, Cepheid, AG, and Kilonovae light curve, so that you can see a bit the cadence and so on the plots, you can see the red bar, which corresponds to the trigger. And for example, you can see with the SN1A example that given the cadence and the number of passband, it will be very important to use properly this 6 passband information because looking at each passband individually will be very tough to give some proper classification. Okay, so here I will present a bit the different classifiers which have been developed inside Fink. Everything has been done on ELAsTICC V1, so nothing I will show is V2. And we've been training on the first year and testing on the second 2 year of data. And also everything will be written in a paper which is in preparation and you should see at some point. I mentioned the SuperNNova, and which is done by Anaïs, and that probably a lot of you already know, and also a small classifier which I did, which is an IGN classifier, which is very simple based on statistical features. I just mentioned them, but I won't talk about them because I have limited time. I will mostly focus on the early Supernovae 1A classifier, which was developed by Marco Leoni and Emily, and which I helped them at the end. A Superluminous Supernovae classifier, which I developed and with the help of Stéphane Blondin as well, to get some insight about what I am actually classifying. And a CATS classifier, which has been developed by the Brazilian Fink team and is a deep learning broad classifier. Okay, so I will start with the early Supernovae 1A. So this classifier currently already exists and is implemented inside Fink and is working on ZTF data. And the challenge here was to adapt it to work on LSST data, because the challenge, as you can imagine, is that the cadence is much lower, and if you want to make some early classification, you have to be smart. So what it does essentially is that it performs just a sigmoid fit. So just for the light curves on the rise, anything which is already going down, it discards. It's just interested in rising objects. And if you want to make some early classification, it was fine before with ZTF because you make a fit of the G band, you make a fit of the R band. It's not too crazy, and then you get some kind of results. But now it's difficult because if you want to make a fit of the 6 band, you will have a problem because your object would already be down before you can fit everything. And so the solution we adapted is to make some kind of multi-passband fits to make use of all the information, much like Roy presented in the laser broker. So we use what we call a rainbow fit. It was one of my work during my PhD. And the idea is that you fit a two-dimensional surface on your object instead of fitting multiple one-dimensional fits for each passband. And you just assume SED, so a black body in this case, and then you get you choose some parametric bolometric flux and some parametric temperature evolution. And that way you have a full description of your physical objects, including some color information, which is very useful to fit. So it also allows for early classification because you need much less data points to fit such thing. So this is the kind of results we got. Here you can see that with a threshold just to 50% because it's a random forest. Just random forest trained with these features and extra features. Anyway, we get 70% efficiency, 70% purity, which is rather good. And the point with early classification is often that we would like to take a spectrum or make some follow-up. And so to that regard, we would like to have purity as high as possible. So what you can do is to tweak your threshold. You could go up to, for example, 85% purity at the expense of efficiency. So you will miss more, but given the amount of data LSST will produce, it might be a still interesting trade-off. Okay, now I'll move on to the Superluminous Supernovae classifier, which I worked on. So it is again based on some fits of light curves, but disclaimer, this is not using rainbow, and it is unacceptable. It should do. The only reason it's not is because I still didn't find any time to change it, but as soon as I get some time, it will be upgraded to some multi-passband fit because it gives much better classification in all the tests we made. So anyway, so it's doing some independent fits, which it should not, and it is using this function, which you can see down there. This function is interesting because it's not found anywhere in the literature. In fact, it was obtained using some symbolic regression algorithm I worked on. So the idea is that given a set of examples that I give to my algorithm, it will output me the most optimal parametric equation to describe the data. I will not talk more about this, but if you're interested, please come talk to me. I would be happy to talk to you about this. Maria just showed you some of the objects that the SNAT team found, and in particular, the Superluminous Supernovae pair instability candidates. And in fact, this is the object I used to find this equation. So I figured out, okay, let's try to use it as a classifier, and in fact, it gives super good results compared to other parametric functions. And so with this, plus some color information, some statistical information, and some metadata, I get such classifier using, again, random forest. So as you can, oh yeah, this is the confusion matrix, which is indeed confusing. And what is happening here is that each square is divided into two. The top part is normalized on purity, and the bottom is normalized on efficiency. So what you see is that we get some super high purity with 91%. So we are very confident in what we say are superluminous supernovae, but we miss a lot of them. Again, with LSST data, we're probably interested in high purity, so it's still fine. And finally, I will mention the CATS classifier, which is a deep learning classifier. You can see here the architecture. I can basically not tell you anything about this. I don't know deep learning, but you can see anyway that the results are pretty good, and it is not classifying subtypes of objects, right? It's classifying the broad types, so the SN-like, fast, long, periodic, and non-periodic. So the results are good, but one thing we can think about, since it's classifying broad classes, is to combine it with smaller classifiers. And we did some tests. with the superluminous supernovae one. So the idea is that everything which is classified as long by cats, we would give to the superluminous to get further classification. And that way we can combine the classifiers. And this is the kind of result we get, for example, with the superluminous. We can see that the purity goes up to 96.6%, so really crazy high, which means that if we combine both classifiers, we are basically certain of our classification if it says it's superluminous. But again, it's at the expense of efficiency. So all these choices are made by the expert, which knows what he wants, and if he wants more completeness or more purity. Okay, so conclusion. We've learned a lot about ELAsTICC in this challenge. And in fact, we in particular learned that going from ZTF to LSST is not a trivial task, not at all. And in fact, we maybe think that it's only about the data volume, but it's not. It's also about the nature of the data, the fact that we have multi-bands we need to care about, the fact that the cadence is lower. But it's also about the data volume, because it gave us quite a lot of opportunity to upgrade and optimize the models and the classifiers to be as quick as possible. So yeah, simulation overall are a good way to prepare, because we have access to some classes of data which are maybe rare or we've never seen, like the parent stability. And finally, even if all these classification metrics are good, ELAsTICC was also a good way for the brokers themselves to prepare their communication between Vera Rubin and the infrastructure themselves. So just for this, it was already a success. So thanks.
Thank you very much. Okay.